I'm Graham Sutherland. I work for a company called Portcullis in London, and I'm going to be doing a talk about crypto and breaking it without all of the ridiculous maths, which I know everybody hates. So, first off, yes, who am I? Graham Sutherland, you know that already. So, G Sutherland on Twitter. Been at Portcullis for about 9 months now. Used to be a dev. Was always into security, doing it in my own time. Eventually decided I didn't really like being a dev anymore, and then moved along to security as a proper job, and I love it. I like reverse engineering stuff. I like being thrown weird black box systems and working out what they do. I also like electronics as well, so doing all the hardware reverse engineering is kind of cool. I did a talk last year on that kind of stuff. Also like network protocols, and often you'll find there's a lot of weird crypto in there, so that's kind of where that becomes useful in penetration testing. Obviously there's a lot of crypto around, but in reverse engineering weird network stuff, you can often find that there's crypto layers in there that you've got to dig out, work out how they all work, and then work out how to break them. So here's the corporate information. Feel free to read it all down. So the topics I'm going to be talking on today, I'm going to start with a bit of a talk background as to why I picked this particular topic and sort of opinion I have of crypto as a field. Some rules of crypto, because they're kind of important. Notation for dummies. Crypto notation is kind of weird, so go into a little bit of that. Basic crypto concepts, so the core building blocks. Types of crypto and how to attack them. So we're looking at a range of different types of ciphers. Some techniques for identification. So if you're looking at a random blob of binary, whether it's a file or over a network, how can you use that binary? How can you use the changes in that data and what you observe about that to identify what kind of crypto is being used, and potentially even the algorithm, and then potentially even flaws in how that was put together. There's going to be a couple of demos, demo God's willing, and wrap up at the end. And the goal is that you'll all learn a little bit about crypto in the next hour, hopefully. So what am I going to cover? One-time pad, stream ciphers, block ciphers, padding, cipher modes, malleability. So there's a reasonable range there. It's kind of the main stuff that you're going to find problems with in crypto in a practical sense. There is obviously a huge range of other stuff that we could go into, but I only have 60 minutes and I've already got a silly amount of slides. What's not covered? So a lot of crypto courses try and start you off on the classical crypto stuff, so Caesar ciphers and weird substitution ciphers and stuff. You will never come across them in doing proper reviews of proper products. I've not seen one yet. So if you want to learn about that stuff, there's so many resources online to go and take a look, but they're not using modern crypto at all. So the elementary ciphers and things like that. I'm not going to look at asymmetric crypto. I put an asterisk on there because there's kind of a few references to it, but we're not going to look into that. Not going to look into key exchange, not going to look into public key infrastructure, which is a massive topic in itself. Unfortunately, don't have time for hash functions and HMAC stuff, which would have been quite nice to put in, but I just don't have time. I'm going to ignore all the evil TPM, DRM stuff, because I hate it. And I'm going to ignore all the monstrously large protocols because, again, you could write books. I don't know. So this is kind of the problem. I don't know whether you can read all of that, but I'll read it out. This is a quote from a PDF from a Microsoft employee who writes a lot of very funny PDFs. There was one, I think this one was actually on Reddit's RNetSec recently, which is where I find it. So sometimes when I check my email, I'll find a message that says, talk announcement, vertex-based elliptic cryptography on n-way Bojangle spaces. I'll look down at the abstract for the talk, and it'll say something along the lines of, it is well known that five-way secret sharing has been illegal since the Protestant Reformation. However, using recent advances in polynomial time Bojangle projections, we demonstrate how a series of peers who are frenemies can exchange up to 5 snide remarks that are robust to Bojangle chosen plain text attacks. I feel like these emails start in the middle of a tragic but unlikely to be interesting opera. Why exactly have we been thrust into an elliptical world? Who exactly is Bojangle? And why do we care about the text that he chooses? And if we care about him because he's abducted our families, can I at least exchange messages with those family members? And if so, do they have to be snide? So the kind of point here is that you find a lot of crypto papers, and these crypto papers, you will open them up and there will just be a wall of text and maths and notation that you have no idea how to read. And there's not really a good introduction to the notation. There's no sort of bottom-up look at the maths that is particularly all in one place. There's a lot of scattered information. And the crypto field in general tends to be, it feels a little bit like a boys' club. You know, they don't want these outsiders in. They don't want people asking these questions because it takes time and I've got other things to do. So it becomes a little bit difficult to try and get into. And obviously, it's got this reputation for being really difficult and being really full of maths, and people don't really want to learn that stuff. But the thing is, it doesn't need to be that way. So why is crypto hard? There's maths, big names, big words, complicated stuff. It does take some time to learn. It can be a bit confusing. The notation is weird. It's quite alien. One of the biggest pains is that some researchers will use one type of notation, a different researcher will use a different type, and you're sat there scratching your head looking at some weird Greek symbol going, what does this mean again? It becomes very difficult. The community, as I said, there's a lot of internal knowledge, but it's not shared outside that field. That is changing. I'm not saying that all of cryptography is like this, but it's a general trend. And it's very punishing. If you get something wrong, really bad things can happen. I mean, I'm sure you've seen all sorts of news articles about, you know, political dissidents getting owned because of their crypto being bad, and then that resulting in really nasty things happening to them and their families. But again, it doesn't have to be hard. It doesn't have to be full of the crazy hieroglyphs. We can explain everything clearly. We can, ahead of time, just put our hands up and go, okay, this is what this means, and now I'm going to use it in this way. And that wouldn't be a problem. Doesn't have to rely on pure maths. It is involved. If you want to look at if you want to play with the proper professional ciphers and you want to be doing proper cryptanalysis and trying to work out new attacks on like AES and stuff, then yes, you're going to have to learn the maths because that's how it works. But if you're just a pen tester trying to break an implementation, you don't really need that stuff. So as I said, we can describe things, we can be standardised about it, we can put our sort of cards in front of us before we start putting all these crazy hieroglyphs over. And learning crypto is easier than learning to code. And that's something that I will absolutely tell you, because I worked as a developer for 2 years. I spent most of my early life learning how to code. Crypto is easier. It doesn't take as long. So there's 5 important rules that I'm going to set forward about crypto. These are rules that I have made up. They may not be accepted by certain cryptographers, but they're kind of a very vague overview of what I would say you need to sort of stick to with crypto. So the first one is custom ciphers are the devil, because custom ciphers, if you've built something from the ground up that you say, oh yes, this is secure, good chances it's not. For example, one of the ciphers that was written for doing, I think it was GSM crypto, that was a proprietary one, got broken in like a couple of weeks. Some of the, I think there was an NSA one that was, I think was top secret or something for ages, and then they declassified it, and then somebody immediately found a flaw in it. So yeah, you have to have all these peer reviewers look over it, and all these cryptographers. It's the many eyes principle, the same sort of thing that's pushed with open source. Number 1, Cipher needs to be secret. It's not Cipher. Basically, if you're trying to hide your code that does the encryption, there's no point in doing that. Someone's going to reverse engineer it. You know exactly how it works, and they'll find out how to break it. So what should be secret is the key. The cipher should be all public. You can go and tell somebody, oh yes, this is what I do, this is what I do, this is all the operations that I do, but you can't know my key. And if your data is still secure after that, then you've got a good cipher. Know what you're doing. So that's a nice little XKCD comment that's kind of relevant here. If you don't know what you're doing, if you're just like XORing random stuff together for whatever reason, and you don't really understand why you're doing that, it's probably going to result in bad things. Even if you're using like really well-known ciphers, if you're doing weird things with them and you're not really sure why you're doing it, it's probably going to be insecure. This one's kind of a quote. I think Bruce Schneier originally said this, but basically you can write ciphers that you can't break yourself really easy. It's really hard to make one that not everybody else can break. And peer review is king. Just get everybody, if you make something new, get people to look at it, because somebody else will spot something that you missed. Even professional cryptographers would never dream of publishing something and using it without having all this peer review. I mean, some of the algorithms that we use today have seen thousands and thousands and thousands of people looking at it for years, and they're only just becoming accepted as standards because they've been around for a long time. So the first thing we're going to do is show some basic logic notation. So there's going to be some like logical operations that I'll be explaining. So this all kind of comes from electronics, where logic gates are basically built together out of transistors. So what we usually say is the inputs to a logical operation are A, B, C, D, whatever. Output is usually called Q. It's not called O because it's 0, and then people get very confused when you're writing these things down. So use a Q. Arbitrary values. So if I want to say we're going to add any number we like, pick a number, we can stick it in there, that will do. We'll refer to that as X. And there's two forms of equality. It's not just a normal equal sign. So there's a normal equal sign, like you would see in an equation. There's a triple equal sign, which means it's an identity. So you could say 1 has an identity of 1 because it's always going to be true. So if you've got certain logical operations that you want to say have this identity, so for example, if you do this and then this will always be the result. That's when we use triple equals. And that's the most complicated bit of notation, really. Basic crypto notation. This is slightly different. So M will always be the message, which is the plain text. C is the ciphertext, which is the encrypted message. So, yeah. K is key, which is secret, you don't want the bad guys to get that. E of MK is an encryption operation. So if I say E of MK, that means you take the message and encrypt it with the key. And then that gives you C, which is the ciphertext. The reverse. D of CK. So ciphertext goes in with the key, decryption operation, output is M, so you get your message back. And whenever I'm going to refer to like bits or bytes of a message, I'll use subscript. So M0 is the first element in a message, so it could be the first bit or the first byte. M1, obviously the next one. And N is the nth of a bit or byte. And that's all the notation. So XOR is kind of important. It's a building block. So it has this cool property, which is that it's reversible. So if I take a 0 and XOR it with a 1, I get 1. If I take that 1 again and XOR it with 1 again, notice the 2 are the same colour, green ones, you get a 0 back. So basically, if you keep XORing the same value, you basically just flip one and the other. So you can reverse it back. So if you take a value you know, and another value you don't know, XOR 2, XOR it again, get your original 1 back. Useful. And as you can see in crypto, that becomes quite useful. It's got this kind of cool statistical property as well, which is that if you know the output, you can't possibly know the values of the inputs. You have to know 2 of them to know the third. Because they have a 50-50 chance of which ones they could be. So if you've got a 0 on the output, it could be a 1 and a 1, or a 0 and 0. I'll explain this one a bit better in a bit. And the number of 1s and 0s, and I think I might have these slides backwards. There we go. So 0, 0, output's a 0, 0, 1, output's a 1. So XOR means exclusive OR. So basically an OR gate would basically be, if either of these are on, if either of the inputs are on, I will give you a 1 on the output. The difference between an XOR and an OR is that if you put both of them on, an OR will still give you a 1. An XOR says it has to be one or the other, it can't be both, and that will obviously give you a 0. So we use this symbol. It's a plus and a circle. Well, I'll just say XOR. You will see that in all sorts of cryptography papers. That's the standard notation. So A XOR B equals Q, which is this table on the right. Now, if you take any value and you XOR it with itself, you'll always get 0. So notice 0 XOR 0 is 0, 1 XOR 1 is 0. So that's an identity. So that will always happen. And also, if you XOR anything with 0, you'll get X. So 1 XOR 0 is 1. 0 XOR 0 is 0. And there's this reversibility thing. So if you XOR A with B, and then again with B, you get A back. And then the same again, if you XOR A with B, then XOR it with A again, you get B back. Which is quite useful. So if you want to do like reversible encryption, XOR becomes useful because you can do one operation and do the same operation again, and you get the stuff back. Yeah. Give pairs, give 0, non-equal pairs, give 1. That's not important. So one-time pad. You've probably all heard of it. It's a perfect cipher. You can't break it, but it's also pointless. So we define it as the ciphertext equals the message XORed with a key, with some caveats. The key has to be the same length as the message. The key has to be perfectly random, and I mean perfectly random. The key must always be unknown to attackers, so even in 1,000 years it has to remain unknown to attackers. And you can only use it once, ever. Use it again, you're screwed. So this is unbreakable due to the properties of XOR. So there's this statistical property that says you can't know anything about the inputs just from knowing the output. And there's also no way to verify correct decryption. So if you change the key, you'll just get different output messages. There's no way to prove that that was the real output message, the original message. And it's one-time pointless. First problem, cracking a perfectly random key is almost impossible. Random number generators, they can't do it. You can make things that are pretty close to perfectly random, but it's very, very difficult, and especially in large amounts of data. So if you want to use one-time pad on 1 gig file, you've got to make 1 gig of perfectly random data. It's not going to happen. Second problem, key distribution is difficult. You need to be able to securely agree on a brand new key that's the same length as the message for every message, which becomes a point slightly weird. Yeah, you can't ever have the key discovered by an attacker. You had a way of doing this. Why not distribute the message rather than the key? Because if it's the same length, if you've got a perfectly secure way of sending this key, you might as well just send the message. So one-time pad is completely pointless. So here's the two-time pad, which is also completely pointless. Same mechanism, but you just reuse the key. As I said, this is bad. So ciphertext A is message A XORed with the key. Ciphertext B is message B XORed with the key. Same key each time. If we know both the ciphertext, which you've got to assume that the attacker does, then we can XOR them together, which is kind of weird. Because if you XOR the two together, what you get is message A XOR the key, XOR message B XOR the key. And if you remember, there was that identity before that says if you XOR the same things together, you get 0. So then what happens is you get message A XOR message B, because the two keys cancel each other out. You get a 0. So now, just by knowing two ciphertexts, you actually know the XOR of the two plaintexts. And that might not seem that useful at first, but it'll tell us which bits of the two messages are equal. And I shall demonstrate this in a minute. In fact, I'll demonstrate this right now. And as I said, demo God's willing. So hopefully you can all read this. So what we've got is a message at the top. Second message, that's message A, message B. We've got a randomly generated key, and just to prove that it is totally randomly generated, I will just So what we'll see here is the message will go in the top, we'll get a second message, we'll XOR them both with a key as a two-time pad. It'll show us the two ciphertexts, and then we'll XOR the two together, and we'll see what the result is. So, let's see. So, anybody want to shout out a word? Oh.
Security.
Security. It's kind of weird doing that. Another word. Same length, preferably. I'll just put these. Is that right? That's right. Probably. There we go. Right. So we've got these two ciphertexts, and if we don't know this key, then we can't decrypt them. But if we XOR the two ciphertexts together, oh yeah, that's a really bad example. That was a really stupid example. Sorry about that. Right. Well, look at that. So we can actually tell which bytes are the same without ever decrypting it. So we can show that given two ciphertexts, we know which bytes are equal. In fact, we know which bits are equal. The reason it looked kind of weird in the last one is because only certain bits were equal. So therefore, when you looked at it, it looked kind of random in hex, but if you looked at it in binary, you'd see a lot of zeros. So yeah, so we'd be able to tell just by being given this that only the last byte is different between the two, and obviously that's bad for security. Oh, excellent, I've lost where I am in my slides. Okay. Oh. My apologies. You can blame Windows. I'm not going to blame Windows, but you can. Right. Now, no plain text attacks are kind of interesting in this as well. So we can further the previous attack. So at the moment, we only know which bits are equal, which is kind of not really, it's good, but it'd be nice if we knew what the original messages were. So if we know that the two messages, when XORed together, will reveal which bits are equal, what happens if we know one of them? So it's just XOR again. So if we XOR it, that result, with one of the messages, we get the other message. So if you know one of those messages, and you reuse this key, or even parts of one of these messages. So for example, if you know that in the first packet, you will have a header, and it's static. If you XOR it with that, you can find out the values of the bytes in the same positions in the second message. So obviously, if you've got one type of packet and then another type of packet, that first one might be static. The second one might have all sorts of secret information at those positions. So you can pull that sort of thing out, which is kind of fun. So that's the formal thing. Message A, XOR message B, XOR message A again, gives you message B, just like we showed before. So yeah, as I said, structures make this easy. Now, I want to make one-time pad useful. So instead of doing a one-time pad, imagine instead of having to make a key that's really, really, really big, same size as your message, instead you have a little key and then you stretch it. So you take this little key that's got a lot of entropy in it, it's really, really random, and then you stretch it out into this big long series of random numbers that are based on that key. And that's basically a random number generator with a seed. So you take a random number generator, take this seed value to make sure that it's actually random, and then it just outputs this long, really, really long sequence of numbers, and they're all random. Hard to predict. Now, as I said, now one caveat to this is you probably know rand from libc, empty rand on PHP, things like that. These are just very basic random numbers that generators. They use things like Merce and Twister. There are what's called predictors for these, so there are algorithms out there that will be able to break them. What you want is a cryptographically secure random number generator. It's called a CSPRNG, but I'm not going to refer to it by that name because I will just trip up on it every time. So yes, it has the seed value. It seeds key. You can use the output like the empty key, and it's called a stream cipher, which you've probably all heard of. So RC4 is a stream cipher that does exactly that. So stream cipher is a generator, G, that takes in a key, and it outputs a set of random numbers. You XOR that with a message, and you get yourself a ciphertext. And that's as simple as it. So step 1, load the key into the random number generator. Step 2, generate a random byte. XOR that byte with the next byte of plaintext. Write it out to your cipher string. Repeat until we're done. and then you've encrypted something. Decryption works exactly the same way, because if you remember, the XOR is reversible. So if you put the same key in, you get the same sequence of random numbers back out, and therefore, you can just XOR them over again.
Sorry.
It's a loud text tone.
I'm sure I turned it off.
That's fine. Right, so as I said, decryption involved in that. Yeah, we call the random numbers produced by this RNG a key string. The construction of it is as strong as K is random, as the RNG is good, and as K is secret. So as long as K is secret, as long as it's unpredictable by an attacker, and as long as your random number generator is well formed, it'll be nice and secure. And you can theoretically encrypt an infinite amount of data based on one tiny little key. There are caveats to that. If you did that, you would not be very secure. But we're talking about you can encrypt gigs with like a tiny key. You only have to generate 32 bytes of key or 16 bytes of key if you've encrypted a gig of data. It's much better than one time back. And now we're going to break them. So, as I said, it's all based around how strong the RNG is. If you break the RNG, you break the cipher. So generally what we're looking for is statistical skews. So if you're looking at the output from a random number generator, and you discover that the first 64 bits have a bias towards outputting a 0 rather than a 1, you can guess that about 70% of the time, that bit, each individual bit will be equal to the plaintext value. But obviously this is based on probability. So if you're looking to brute force the message, if you know some kind of form that it will take, maybe it's got checks on it, you could brute force through those much better than having to go through every possible value. You've got a 70% attempt there. Obviously it might be still computationally expensive, but it's faster than having to do the full random, I don't know what this message was at all, and therefore that's considered a break. So yeah, the most useful attack, most of the time, for an RNG is what's called a predictor, which is a function that takes a sequence of numbers that's come out of the random number generator and tells you the next one, without knowing the seed. So if you don't know the key, but you get a whole bunch of numbers out of this random number generator and then pass it into this function, it will tell you what the next one is. If you know what the next one is, then you can just decrypt everything, which is kind of useful. And also kind of horrible for people who are implementing crypto. Formally, it's this horrible monstrosity. I'm not even going to explain this because, and this is part of one of the reasons that I'm doing this talk, that horrible monstrosity means that given all previous outputs, I can guess the next output correctly significantly more than half the time. It's kind of one of the reasons that crypto papers are really difficult to read, because they do things like that, and then it means something as simple as that, and then you go, why are you doing that? Right, there's an easier way than doing all of that. As a pen tester, you probably won't have to. You won't have to break RNGs. You won't have to mess around with any of that kind of stuff. You won't have to write a predictor. Instead, you can break the implementations. So most of the time, custom crypto stuff that you'll see is badly done. For example, forgetting that the same, if you put the same key in every time into the RNG, into the stream cipher, you'll get the same cipher stream back out. Get the same key stream back out, so you get the same sequence of random numbers. People forget this, despite the fact that it's how it works. It's the core principle of how it works. So you get key reuse. So if you reuse the same key for the same message, for different messages, same key twice, it produces the same sequence, and therefore we're back on this known plaintext problem, which is if you know the plaintext of one, you can decrypt the other. It's bad. So the key reuse is bad. But key reuse is actually very useful, because let's say, for example, you're using a stream cipher to encrypt a big zip file, and you use a password, and the password is hashed, and then you use that hash as your key. Well, what happens if you take another zip and give it the same password? That would be really useful for a developer. I'll just get to use that and then it's done. That's not a problem, is it? Oh wait, yeah, they've just decrypted all my data. So we need to come up with a solution for this. And the solution is what's called an initialization vector, also called a nonce value. Nonce means number used only once. There is a difference between a nonce and an initialization vector, which I shall probably get to in a second. So an IV ensures uniqueness. It stops this problem of the same key being used twice. It doesn't produce the same output. It doesn't produce the same set of random numbers as when you put the same key in. But as long as you know the IV when you're coming back, you can still decrypt it with the same password, which is useful. So it's loaded as a parameter into the random number generator. The same key, same IV will produce the same random numbers. The same key, different IV will not. And therefore, you run out of this problem. So it patches the reuse hole. With the caveats. IVs must never be reused themselves, they must be unique. They should be random. In some cases, you don't need a random number. So it doesn't have to be random, and that's when it's called a nonce. And IVs don't always have to be secret, which is kind of nice, because obviously if you're only having to exchange the key and the IV can go out publicly, as long as they know the IV, it's fine. So you're not running into all these like key distribution problems. And you can use the same key pretty much as many times as you like, as long as you use a different IV for every message. And then you get IV reuse because people are going to do things randomly. So what happens is you run into these problems where an IV gets reused, and then an attacker can capture ciphertexts and decrypt them, because if you use the same IV and the same key, you produce the same random numbers, and then again we run into the same known plaintext problem or the XOR problem where you can see that the messages are the same. If you have a really short IV and a lot of messages, you can run out of IVs, and then you've used all of them, and then you're screwed, because unless you change the key from there, you can't have a unique IV because you've used them all. And it can be forced by an attacker, because if they have a way of forcing you to tell them a new IV, eventually you'll run out of your pool of IVs. And in fact, there's this kind of weird thing called the birthday paradox, and this is literally the hardest thing to wrap your head around in this whole talk. Took me a while. Essentially, it states that in this room, there will be probably at least two pairs of people that will share the same birthday, despite the fact that we don't have more than maybe 50 people in here. Even though there's 365 possible ones, you would think that if you just randomly pick 50 people out of 365, you probably wouldn't get a collision of birthdays. In fact, there's a 99.9% chance that with there will be a shared birthday in a crowd of 75 people. And with only 23 people, there's a 50% chance. That seems kind of counterintuitive. But what it does is it works on diminishing probabilities. So as you add more people into the group, more birthdays are taken on. Everybody has a birthday. So therefore, the number of birthdays that you're left with gets lower as you add more people, which means that every time you add one more person, their chance of colliding with somebody who's already in the group is higher. And this diminishing probability, opposite of diminishing probability, causes this weird effect. And you're probably thinking, well, what the hell has this got to do with crypto? Well, the interesting thing about the birthday paradox is that if you've got this big pool of IVs and you don't want to reuse them, you don't want a collision. But if it turns out that it's actually surprisingly easy to get a collision if you just randomly pick them, that becomes a problem, because even if you've got this, what seems to be a big key space, like a 24-bit IV or a 32-bit IV or even a 60-bit IV, a 64-bit IV, you might accidentally bump into another one of these IVs if you're doing a lot of messages. Eventually what happens is you run down these probabilities, run down, and eventually the probability becomes very, very high that you're going to reuse one of them. And that's all based on the birthday paradox. So yeah, so it works out interesting. So web failed because of that, and certain other issues. So it has a 24-bit IV, the RC4 stream cipher, and what happens is, so for 24-bit IVs, if you pick them totally randomly, after only 10,000 new IVs being created, there's a 95% chance of hitting a collision. And that's where the paradox part of it comes in, because that seems counterintuitive. So what happens is, an attacker comes along, sends out a bunch of probes and goes, oh, I want to connect, give me a new ID. I want to connect, give me a new ID. I want to connect, give me a new ID. And eventually they'll collide. And what will happen is, they'll know the ID, they'll see the ID of another message going across the network, and they'll go, oh look, these match up. And then they've got exactly the same values. And on top of that, because the header packets have a known format, you can guess what the values are inside there, and then XOR them across and decrypt the traffic, and then bang, it's broken. It's a little bit more complicated than that, and some of the more advanced attacks that came out later that can break web in like 30 seconds on a network with only like one person on it, doing pretty much nothing. They very much expanded on this attack and produced a very, very clever technique of doing it, but that's the basic way that you can break things like that. So fixing the ID problem, well, for a start, you want bigger IDs. So the bigger IDs, the longer it takes for you to run into this birthday paradox problem in general. But with it being a probability, you never know when it's going to hit. You could get a random number generator that produces the same ID 20 times in a row. It's just really unlikely. So incremental IDs is potentially a solution. In some cases, you can actually do things like this. But again, you would usually call it a nonce because it's not random, it's just incremental. Or you could have the first half of it random and the second half of it incrementing. But there are problems with this. There's a thing called a related key attack that certain ciphers fail to. I'm not going to go into that because it's kind of complicated. But basically, it's one potential solution. It's not a great one in every case. Generate IDs in a way that ensures no collisions. So for example, you could, if it's only a 24-bit ID or a 32-bit ID, just keep a big table and then randomly pick them. And then when you pick one, remove it from the list. And when you run out, change your key, because obviously you've run out of IDs. Key cycling. This is what's called temporal keys. So newer Wi-Fi systems use this. I think WPA2 and WPA both use temporal keys in different ways. A temporal key is basically, instead of having this, so you have this thing called the root key, which is derived from the Wi-Fi password, or whatever password, which then allows you to exchange a temporal key, which is a temporary key that only runs for a certain amount of time, and then obviously helps reduce the problem of IV reuse. And another way entirely. Stream ciphers aren't the only thing you can use. You can also use these things called block ciphers, which you may have heard of. So what they do is they take your plain text, instead of bit by bit XORing them across, they take this whole block, a fixed block size of plain text, and perform what's called a transform line. And that outputs a block of ciphertext. And that transform takes the key and encrypts it in a certain way. Unlike stream ciphers, the ciphertext and the plain text bits don't actually have to align up, in fact they probably won't. So think of it a little bit like an anagram. You can fit them around in this side of this block, and then you can also change the values of them in certain ways. So the famous one's a serpent to fish S. This is old 56-bit keys or blocks, can't remember. Anyway, it's old and crap, but 3S kind of works. Yeah, block cipher operator. So we've got two functions that we'll define here. E of MK is an encryption, so E, the encryption transform, takes a message block M and a key K and it outputs a ciphertext block. D of CK is exactly the same thing. So as we said before, these are the decryption operations and the encryption operation. But in this case, they work on blocks which are fixed size, so it might be a 128-bit block. Each input block, as I said, there we go. Always preempt myself on these damn things. So first we encrypt the first block. So ciphertext 0, so that's the first block. Ciphertext is equal to message block 0 encrypted with the key. Encrypt the second block. Again, C1, Z, and 1K. Decryption basically works in reverse. You decrypt ciphertext block 0 with the key, and you get back your message. Send again to the second block. And one of the cool things with this is you can do everything in parallel. So notice that there's no reliance in these two between each other. So So you can encrypt all of these blocks in parallel. So you could have like 16 cores all burning along really, really fast, encrypting each of the, doing these block transforms all independently, using the same key, and you output everything. So it's really fast. And it allows you to do random access. So you just go, okay, I want block 67, decrypt block 67. Easy, which is great for things like if you wanted to do just decrypt a single record or say disk encryption. But this is kind of problematic, and I'll come to that in a minute. So diffusion and confusion. Hopefully not too much of that in here. These are two properties that we try and put into block ciphers, or well, when I say we, I mean cryptographers. So they use these two core concepts. Now diffusion is about, if you take a block, distributing randomly that information across the block. So think of it as like an anagram. So it's hard to make sense of O, B, C, and A than bacon. So it flips these around. So it's all the same values, they've just been moved around. Confusion is about modifying the values. So you're trying to obscure their values rather than just moving them around. So if I type the key to the right on the QWERTY keyboard, I get NSVPM instead of bacon. So again, this makes it harder to understand what the original values are. And if you go and put both of these concepts together in a long loop, and you use a lot of these different transformations, it can actually produce a very strong cipher. And you will find that if you look at any of the descriptions of major block ciphers, for example AES, you will find that both of these things are referred to. So you'll see things like what's called S-boxes, which are substitutions. So they basically take an input value, look it up in a table, and output a different value based on that. And that is a confusion, because obviously it's trying to separate the input value from an output value. Diffusion, you'll see that they've got these things called block rotations. So let's take the bits, put them in a big square, rotate it round, and then output them again. So obviously, based on, and then all of these operations are based on the key. So they're based on certain properties of the key. So because you don't know the key, you don't know how many times these certain operations have been done, you don't know what values they've been substituted with, and it becomes very, very difficult to trace that back without knowing what the key is. And that's what brings the strength of a block cipher. There are other properties, of course, but these are just the two main simple ones to understand. Now, one of the problems is, if you've got a fixed length block, what if your message isn't the fixed length? What if it doesn't fit to this fixed length? Obviously, you can split it into more blocks, but what if your block size is 16 bytes and you've got a 3-byte message? It's not really going to work very well. So what we do is this thing called message padding. Yeah. Now, there's padding schemes that can do this kind of thing. And they essentially add more data onto the end of the message in the plain text before being encrypted. And based on doing that, the padding can then be stripped off on decryption. So you take the message, you pad it to the right length so that it fits into these block sizes, encrypt it, and then later decrypt it and pull the padding back off. The way this padding works is different depending on the padding scheme you use. The most common one is called PKCS7. So basically it adds the value that it adds on the end is byte level, what's called byte level padding, which means it adds bytes, not bits onto the end. And the value of each of those bytes should be the number of bytes that there are. Make that slightly easier. If you've got a 4-byte message, not F, not 2, not A5, we would stick 4 4-byte bits. So 4, 4, 4, 4, and that makes your full 64-bit block. Really easy to strip back off because you can verify that all of those bytes are all 4s. The last one should be the same as all the rest of them. You can verify the length, it's quite easy. Now there's other padding schemes, ANSI-X 923, ISO 1126, and it goes on. You don't really need to know about these, you can look them up on Wikipedia if you ever run into them, but they're all kind of interesting. Now, there are different modes of operation for block ciphers. The simplest mode is called ECB, electronic code book, and that's the one I already described, which is where we take each individual block and we transform it separately and then we output it. There are other modes as well. CBC, cipher block chaining, CFB, cipher feedback, OFB, output feedback, CTR counter mode, and XTS, which is a disk encryption mode. There's another one called XTX as well, which is used in TrueCrypt. They all have different properties, they all operate in different ways. Now, the reason for these existing is because ECB is broken. So, when I showed you ECB, which is the one where they're all individually transformed, turns out it's not actually secure. So even if you take this really secure cipher, like AES or Serpent, and you run it through ECB mode, if you encrypt more than one block, it's not secure. Basically, the data patterns inside the message end up not being obscure. And this is the proof. And you may have seen this picture on Wikipedia. It's a great picture. Basically, this on the right is an ECB encrypted picture. So they take the left picture, they encrypt it with AES. This is actually AES. But because these values on the left, you have these big sections of white, which all have the same values when put as a bitmap, which means that the blocks are actually the same. So even though that the output of each block looks really random and you can't decrypt it, you don't know what the original values are, because the same blocks are encrypting to the same values when you're using the same key, what happens is you get this weird pattern effect. So you can actually see what's going on inside the image without ever decrypting it. So this is where demo 2 comes in. I really hope I don't have to flip through all my slides again after this. Here's demo 2. Remember this control face? Right, so this actually is going to encrypt an image using AES. So what I'm going to do is I'm going to take a password, just any random word. It's going to hash it. It's going to hash that value, turn it into some big long value that I can use as a key. So in this case I'm using #256 to produce a key. And then it's going to ECB encrypt it. And the result is going to be that it then takes a known bitmap header and sticks it back over the top of the data just so that it can recognise it as an image. But all of the image data isn't changed, it's all encrypted. And then it's going to show that picture on the right. Now, somebody shout out the password so they know I'm not cheating.
Password.
Planting. I like that one. I can't spell it. Excellent. Right. Now, when I encrypt this, oh look. So we've encrypted with this password, and you can still see the troll face and these weird little patterns on the right. I think, for no particular reason, this one actually comes out with a really cool effect. Yeah, so you can actually see it really well there. So that's actually encrypted with AES. That's a 256-bit AES encryption. You wouldn't think it, would you? That's a 256-bit AES encryption, and you can still see the damn image. So somebody can go, all right, oh yeah, it's all encrypted. It's all encrypted. So if you hear somebody say, oh, it's all encrypted, you can't see it. Just laugh at them. You have my permission to laugh at them. And then show them that picture on Wikipedia. So if you look for block cipher modes on Wikipedia, that picture with the penguin is on there, and it explains it really well. So it's kind of nice. Right. Now, with any luck, I won't have to flip through about 500 slides. Yeah, you click run from current slide and it doesn't. Kind of weird. So anyway, solving the ECB problem. So the identical plaintext gives us the identical ciphertext, but we use the same key. So how do we solve this problem for string ciphers? Well, we solved it by using an IV. So again, the solution is using an IV, but a block transform can't take an IV as a property because a block transform has no concept of where it is in the string. So it doesn't know whether it's 0 or a million. So instead, we change the construction of the cipher, and it's called a mode. And as I said before, there are these other modes. CBC is one of the most common modes you will find. That's probably what it says here, yes. Cipher block chaining. Oops. So it XORs each plaintext block with the previous ciphertext block before passing it to the transform. There'll be a diagram in a minute. Because the first block doesn't have a previous block, we use the IV. So we have an IV that is the size of the cipher of the block for that particular cipher. So formally, ciphertext block N is equal to the encryption of message block N XORed with the previous ciphertext block using K. And obviously, but it will be a lot easier to understand when you see that. So, so you take the plain text in, you take the initialization vector as what it XORs it with for the first block, but with every subsequent block, you then take the ciphertext of the last one, XOR it with the plain text, and encrypt it again. And this causes this propagating effect whereby you no longer have this equal plain text producing equal ciphertext. Now there are problems with CBC. First one is that there's no parallel decryption and encryption because they all rely upon other blocks. So you have to be able to encrypt and decrypt randomly. Wait. No. It means you can't encrypt and decrypt randomly because of the reliance on the previous set of data. So you can do random access reads. You can random access decrypt. You can't random access encrypt. I think I screwed that top one up. So basically, if you write to a block, because it has to know the previous ciphertext block, if you write to a block, you have to re-encrypt all of the rest of your message. So if you want to update the header at the very start of your file, you've got to encrypt the entire damn file again. If you just want to re-encrypt the last one, you can just re-encrypt the last one because there's no subsequent blocks that rely upon it. Now there's this thing called block malleability. It's got caveats to it. I'll explain this later because I've got a little section on malleability. I'm aware that I'm going to read this later. There's no inbuilt authenticity or authentication, so there's no way to check that this message definitely came from someone. And we'll see why this is important later. There's issues with padding. So I mentioned padding on purpose earlier because there's this thing you can do called an oracle attack. So padding on an oracle attack, you may have heard of it. It became quite famous because somebody worked out how to do it in SSL. What it says, what it is essentially you keep tweaking the plaintext when you can send plaintext values, but encrypted with a key you don't know, and then see the result, or see an error based on the fact that your padding was wrong in this message. You can actually start to work out things like plaintext from other messages, or recover the original key. So you can do these padding oracles, which is basically send something where you've tweaked the ciphertext, so a message you know is correct, and then start flipping some random bits in the end of the ciphertext. And that padding will get messed up. And based on the error responses you get from the system, you can start working things out. But it's very complicated. But somebody actually did this with SSL, and it became known as the beast attack. And another one, issues with compression. So you get this compression oracle attack. Well, I think it was the beast attack. Compression oracle attacks, which are basically the same thing, except you rely on the fact that compression changes if you have like repeated values. So if you've got like 600 A's, you can reduce that right down to like only a few bytes. But if you've got really sort of random mangled data, it doesn't compress as well. So based on what data you're putting in, you can start to find out other data that was in your message. So for example, if you can send a message where there's a secret bit that you don't know, but you can append something onto the end of that. If you start brute forcing the message, when your message aligns quite closely with what was previously there, the compression algorithm can work out that those two things are quite similar and compress them together. And suddenly, your message length drops. So you start brute forcing these messages, it gets long, and then drops. And when it drops, you realise that you come quite close to what was something that was in the original message. So you're guessing based on this attack. But some of these issues aren't unique to CBC. So malleable ciphers, mentioned them earlier. So malleable ciphers allow for plain text to be altered in some meaningful way without knowing the key. If you just got a ciphertext and you can mess with the ciphertext and then get somebody to decrypt it with the proper key, without you knowing the key, you can make these changes to the message. So in a string cipher, remember that it's just the message M XORed with a key string. Now, if you XOR the ciphertext with some value X, the output is the message XORed with X. Because as you can see. Before, when you decrypt it, you're just XORing with the key, which strips the key part off, but the XOR with X is still there. So you've actually XORed the message with something without ever knowing the key, which is bad. It's very dangerous because in known plaintext attacks, we can tweak the ciphertext of anything we know. So if we know the position of something, we can actually change it. So if we know there's a number that's going to be a 0 and we want to change it to 600, we XOR this part of the message with 600, and it changes the message without knowing the key. It's also useful for doing side channel attacks on error handling. So if you know that there will be an error if a set number goes above a certain value, you can repeatedly XOR with stuff until you hit that value, and then you know what it is. So then you've got yourself a no plaintext. Then you can. It gets kind of complicated. Anyway, CBC is kind of manual. Ah, what happened there? Oh, well, you've seen all my slides now. Right, so yeah. So if we XOR a ciphertext block with some value, it gets destroyed when you decrypt it because you've totally munged up that bit of that block. But remember that in CBC, it takes the ciphertext from the previous block and XORs it with the message before encrypting it. So when you decrypt it, you do the decryption transform, XOR it with the previous ciphertext block, and then that gives you the message. Now, if with the previous ciphertext block, you've XORed that with some value, when you do the XOR step again, that value gets XORed onto the message. So you've basically done exactly the same thing, apart from with the caveat that you have to destroy the previous block. You can still decrypt everything, but you destroy one block. Now, that might seem a bit pointless, because obviously, if you're doing some sort of network transmission and the packet comes in and it's all messed up, then it's not going to validate it. But that's not always the case. Yes. So that's the most complicated notation I have in the entire thing. So the ciphertext N is created by encrypting a message block XORed with the previous ciphertext block. The message is decrypted by taking the ciphertext, decrypting it, and then XORing it with the previous block. Now, if we XOR it with this extra value, what happens is that decryption step, instead of having this Cn-1 here, you have Cn-1 XOR X, which then produces this XOR with X in the message. Now, surely this doesn't work as easily. Oh, it does. And have you heard of Lux? The Linux disk encryption? Whoops. So it's possible to find non-critical blocks of data adjacent to critical blocks of data. So lol.txt next to your kernel. So if you trash lol.txt, you can change the kernel. You can XOR the kernel. And if you know that the kernel has some fixed bytes inside there, you can obviously start messing with that data quite easily. So the result is that you can modify all sorts of files on the Linux partition, which was really bad. And this actually only came out like a month ago. Seriously. So the solution to malleability. First one, authenticity checking. So you can do a cryptographic hash in something called a MAC construction, which is a message authentication code. Or you can use a block cipher mode that has built-in authentication. You can integrity check your plaintext, so you can do a MAC on a plaintext, but then what if we just change the MAC using that trick, using the malleability trick? So it's not a strong solution. Or you can use a non-malleable mode, XEX, XTX, both disk encryption, hard word to say, disk encryption modes that are designed for this kind of thing. Now there are other attacks that we can do, error side channel attacks, which I kind of talked about earlier, which is messing with the ciphertext and then waiting for checking what types of error messages are thrown out. And often you can find yourself in conditions where you can flip these bits in certain ways and then get certain errors and then get other errors. And based on that, you can start to deduce information about what was inside the message. Padding oracle attacks, as I mentioned before. Compression oracle attacks, again, as I mentioned before, like the prime attack against SSL. Hash collisions on integrity checks. So if you've got a hash, a cryptographic hash, there are certain hashes that are flawed. MD5 is one of them. SSL public key infrastructure kind of fell to this because people using MD5 hashes to verify the authenticity of, or the integrity or authenticity of digital certificates, and then somebody found that they can produce digital certificates that have changed, that have the same MD5 hash, and therefore you get this collision, and you can start messing with valid certificates. So you can take a valid certificate that is valid for this specific domain, say google.com, and then you can change it so now it's actually, with the same MD5 hash, is now valid for, I don't know, google3.com instead. So you've changed this one little bit. Obviously there's a little bit more to it than that. But yeah, so because of these collision issues, you can often find that if you're checking the integrity of something with a poorly chosen hash function, you might end up finding out that people can mess with things and keep the same hash. Related key attacks, which I mentioned before, kind of complicated, but essentially if you do things like if you get a key and then you increment it or like flip some bits each time that you want to use something instead of getting a whole new key, in certain cases you can find that this starts to leak information, but again, complicated. Unidentified cascade interactions. Sounds really complicated, it's really not. Anybody who's used TrueCrypt will know that you can choose things like multiple ciphers for doing the encryption. So it encrypts with one algorithm like AES, encrypts with a different one like Serpent. So it does these in what's called a cascade. In some cases, really interesting interactions that haven't been studied properly. So for example, we know that AES is secure, we know that Serpent is secure, but what happens if you take these blocks and put them against each other using the same key? If you take these block transforms and put them one after each other, if you use the same key, it might turn out that there's some weird, interesting interactions, but again, we're talking about cipher analysis here, which is quite complicated, and we probably know how to do. So, identifying ciphers, I promise I'm nearly done. Ignore goes to the bottom. Identifying ciphers. In general, we want to look at how the data changes when we put new, different messages in. So if we know that we've changed the message in a specific way, how does the message change? So we're looking for obvious patterns, repeating blocks and stuff. So if you know that, like for example, with the demo that I did on ECB, you can see these repeating patterns for when all the plain text is the same, you get the same ciphertext. Look for header data in the values. So it might give things away, like the block size of the algorithm. So you might find that there's a 4-byte integer that says, that actually just turns out to be, I don't know, 128. And that could be the key size, it could be the block size. But it's more information that you can sort of piece things together with. Does a single bit of input change a single bit of output? Does it just change a fixed block? So if you just change a fixed block, sorry, if you change a single bit of input and it only changes a single bit of output, you're probably looking at the string cipher. If it changes a fixed block of information, it's probably a block cipher. If it changes everything after that block, then that might be a block cipher in CBC mode, because obviously you get this cascading issue. Or if everything changes, they've probably been doing something kind of at least semi-right, because obviously all of your data's changed. And if the data is significantly shorter than the data you put in, they're probably using compression. So you can start to identify these potential issues. So these are the kinds of things you want to be looking for if you're reviewing crypto in an unknown network protocol or a file encryption scheme. And match these block ciphers, key sizes, any information that you can get all together into this list of potential ciphers. You can look them up on Wikipedia for all of the common ones, and then you can look at those values and match them across. So putting it all together, yeah, as I just said. So you can use the ciphertext change behavior, so when you change the input, what's the output, to guess the mode of operation or whether it's a block or string cipher. You can use tools like PID's crypto analyzer. This is really cool. Basically, PID, load in a binary, it tells you things like potentially which compiler is used to make it. Has this plugin called Crypto Analyzer, and it looks for all of these special constants that are used in certain crypto and compression algorithms, and it digs them out. And not only does it tell you where they are in the file, it also disassembles it and tells you where they're referenced, which is really kind of useful. So if you're reverse engineering something, you load it in there, it'll probably go something like, oh, it's got zlib, so you know it's compressed, and oh, it's got AES box in there, so you can go, okay, so it's probably compressed and encrypted. So just by loading that binary in, you've already guessed what the crypto is. You can look at patents for software or hardware. That often shows certain things. If patents apply to a particular product, you can often find certain things about the network crypto in there. FCC ID database is awesome for hardware stuff. If you're ever doing hardware reverse engineering, and look on the stickers on this piece of hardware, you'll find this thing called the FCC ID. So in America, when they're sold, they have to pass certain emissions test standards, so electromagnetic emissions coming at them. You can't basically have it blasting microwaves at the user's face. So what happens is when they put these applications to get FCC IDs so that they can be sold properly in America, all of the internal testing documents go onto the FCC database, and then you can look them up online using the ID. And when you look them up, there's like photos of the internals of the hardware, and often what you'll find is people scratch off chip bits and stuff, and you'll find them pre-scratch off, and you'll find all these nice internal bits of information. But you'll often also find out information about any radio communication, and therefore any crypto that's done inside that radio communication. Is really useful for that kind of thing. And general reverse engineering, if you're going to be digging into this kind of stuff as trying to work out how a protocol works when it's encrypted, you're going to want your general reverse engineering skills. So, for example, static analysis, debugging, things like that. So the bottom line, crypto's hard to get right. There's a lot of hidden issues. So as I've showed, there's a lot of different mechanisms that you can use, but then a lot of them turn out to not actually be secure in certain cases. You have to build them in the right way. So most applications and systems tend to be flawed because people made untrue assumptions about these particular things. Like AES is secure. If I encrypt it with AES, nobody can tell what it is. Unfortunately, then you can still see the image if it's ECD. You see the patterns. Breaking systems that use strong ciphers. Oh, just said that. Right. Yeah, in many cases, you can just observe the behaviour of the cipher or the construction to work out what's being used. If you're implementing it, stick to the tried and tested stuff. Try not to put your own custom things in there. Try not to make assumptions about things. Do your research into the implementation of it, and then get everything peer reviewed by people who know what they're talking about. So, for example, Stack Exchange has a sub-site called Crypto Stack Exchange. Go ask questions there. They're all really quite cool with this stuff. I don't know whether they specifically allow you to dump a big binary on them and say, hey, go review this, but they have like chat channels and stuff like that, and they're generally quite nice. You don't need to understand the maths inside the ciphers to break things. You can just look at the logic of how things are constructed. It shouldn't be so difficult to get into crypto. Bit of recommended reading. I like these two books. So, and it's not this is not an endorsement by the company that I work for. It's just I like these books. The Coursera standard crypto course is kind of good. It does have quite a steep learning curve, but it's all like video stuff, like video lectures. It's very nice. The end. I'm very much aware that I've run over by about 10 minutes, but if we've got any very quick questions. Anybody? I haven't baffled you too much. Okay, thank you very much.